Welcome back to The Explainer. Today, we're taking a hammer to pretty much everything you thought you knew about building the world around us. For a really long time, steel has just been brushed off as this expensive metal when people look at their initial construction budgets. But what if that perspective is just entirely backwards? In this Explainer, we're going to explore a massive paradigm shift. We're going to see how steel is actually this highly efficient, endlessly reusable life cycle solution that doesn't just build stronger, safer structures, but actively saves a ton of money and the environment over the long run. Okay, let's dive right into this. Here is our structural blueprint for today. We'll kick things off with the concrete infrastructure crisis, then look at why steel stands stronger, unpack the hidden cost illusion, dive into cutting waste with algorithms, explore the circular steel economy, and finally wrap up with building a sustainable future.
All right, part one, the concrete infrastructure crisis.
So look around globally right now. We are seeing a really disturbing trend of bridge failures, and it's heavily skewed toward traditional reinforced cement concrete, or RCC, structures. They're suffering from early deterioration and require this constant, agonizing maintenance that just completely disrupts our daily lives. Which brings us to a really fundamental, provocative question. What if the absolute cheapest way to build on day one is actually bleeding our budgets dry over the next 50 years? Now, what's really interesting about this slide is the stark contrast in how these different materials fail. For RCC bridges, a whopping 30% of failures are linked just to design and construction flaws, and another 30% is down to pure deterioration. Meanwhile, steel shows significantly lower failure rates across the board in those really structurally demanding contexts. In fact, properly maintained steel bridges are hitting a remarkable average lifespan of 36.2 years before they even need major interventions. And steel suspension bridges? They last even longer. The data is super clear here. Steel just stands up way better to the test of time and stress.
Moving right along to section 2, why steel stands stronger.
So why exactly does steel wipe the floor with concrete in high-stakes environments? Well, it all comes down to a few really extraordinary physical properties. Let's rapid fire through these. Steel has an absolutely massive strength-to-weight ratio. But honestly, perhaps more importantly, it has incredible ductility. Think about it. During an earthquake, an RCC structure can exhibit a brittle failure pattern. It just cracks and breaks, no warning. Steel, on the other hand, acts like a giant shock absorber. It literally flexes. It dissipates the seismic energy without losing its structural integrity. Plus, because steel components are fabricated in a highly controlled factory environment rather than poured on some messy, unpredictable construction site, the precision and quality control you get are vastly superior. Let's put a hard number on that strength-to-weight ratio for a second. Consider this. An extensive SDA-Dodd-Pro computational study actually compared two identical 10-story commercial buildings and found that the steel structure was 38.6% lighter overall than its concrete counterpart. I mean, that is a massive reduction in structural weight. This completely radically shrinks your foundation loads and reduces the inertial mass that those earthquake forces act upon. It just makes the building fundamentally safer from the ground up. But wait, the benefits aren't just structural. They're totally operational, too. That exact same study found that the steel building could be constructed almost 50% faster than the concrete one. Because steel relies so heavily on prefabricated modularity, you completely eliminate those agonizing wait times for concrete to cure. You literally just bring the pieces to the site and bolt them together. And look, in the construction world, time is money. A 50% time savings is absolutely massive. All right, section 3, the hidden cost illusion. Okay, we've got to address the elephant in the room here. Upfront material costs. Yes, steel costs more on day one than concrete, which is exactly why so many projects default to RCC. But you have to think of construction costs like an iceberg. That initial construction cost, that's just the visible tip breaking the water surface. And sure, the tip of the steel iceberg might look a bit bigger on day one, but the RCC iceberg has this massive hidden underwater mass. We're talking decades of constant maintenance, major repairs, midlife reconstructions, not to mention the economic nightmare of traffic detours when a bridge is closed down for months at a time. Steel dramatically shrinks those massive hidden underwater costs. So the crucial point is captured perfectly in a recent IIT Bombay study. They compared 30-meter span highway bridges over a 100-year design life. Because steel requires so few repair cycles and basically entirely avoids the need for a total midlife reconstruction, the steel bridge actually ended up delivering a 33.4% life cycle cost savings. It turns out, spending just a little more on steel upfront makes it vastly cheaper over the span of a century. On to section 4.
cutting waste with algorithms.
Let's pivot for a second from physical economics to some really cool computational breakthroughs. One historical downside of steel has actually been factory waste. The scrap left over when you're cutting standard beams down to custom lengths. This mathematical headache is known as the cutting stock problem. Failing to optimize how you cut these steel beams from standard factory rolls leads to just massive, unnecessary financial waste and a huge environmental impact. For decades, engineers just optimized for the minimum weight of the final building, totally ignoring the colossal pile of scrap steel they were generating on the factory floor in the process.
And this brilliantly illustrates how we're finally fixing that mess. Researchers are now deploying genetic algorithms, which is basically AI inspired by natural evolution, to solve this cutting stock problem. The algorithm analyzes the structural design, groups the elements, and tests millions of cutting combinations to ensure that almost every single inch of the standard steel stock is mathematically utilized to its fullest potential.
And the results? Absolutely staggering. By shifting from a simple minimum weight optimization to this new algorithmic minimum waste optimization, researchers achieved a striking 40% reduction in cutting waste. We are literally computing away the environmental footprint of steel fabrication. It's a real game changer. Which brings us to Section 5, the circular steel economy. Beyond its physical strength and all these fancy algorithms lies steel's ultimate superpower. As the research notes, steel is 100% recyclable and can be recycled indefinitely without losing its physical or chemical properties, making it a circular material for generations. Just think about that for a second. When you build with concrete, its end of life is basically a landfill. But we need to fundamentally reframe how we view a steel building. It is not a permanent disposable fixture. It's merely a temporary configuration of a permanent material. And the coolest part is we're already seeing this beautiful circularity in action today. Take the BedZ Eco Housing Project over in London. They sourced reclaimed structural steel straight from demolition sites. By reusing just 11.5 tons of it, they saved 303 gigajoules of embodied energy and 21 tons of CO2. Or look at the Angus Technopole building in Montreal. It was this old locomotive assembly plant where they adaptively reused 85% of the existing site materials. They kept the gorgeous historic steel framework completely intact to build a cutting-edge modern innovation center. Let's move to the next slide and see how this builds a totally closed-loop life cycle. We produce the steel once, we construct the building, and then a century later, instead of just indiscriminately smashing it down with wrecking balls, we carefully deconstruct it. We unbolt the beams, we test their strength, and we use them again and again. From year 100 to infinity, that exact same piece of steel can serve as a hospital, and then maybe a school, and then eventually a bridge. Finally, Section 6, building a sustainable future. It is time to bring all of these threads together. The physical strength that survives brutal earthquakes, the life cycle economics that save millions of dollars, the genetic algorithms that completely eliminate factory waste, and the infinite loop of the circular economy. The core takeaway of this explainer is simple, really. Steel fundamentally transforms construction. It forces a desperately needed paradigm shift. We have got to stop obsessing over the cheap initial price tag of disposable concrete structures. We have to start investing in the total life cycle value, the incredible resilience, and the endless circularity of steel. So, I'll leave you with this. The next time you drive over a bridge or walk into a skyscraper, ask yourself, are we building for today's budget or tomorrow's survival? The evidence is pretty clear. A sustainable, resilient future is quite literally forged in steel. Thanks so much for joining me on this explainer, and as always, keep questioning the world around you.